In this video, we're going to continue our focus on organic chemistry, organic molecules, and we're going to start to think about the language of organic chemistry. What is the vocabulary that we're going to use? How do we draw organic compounds? Since we are aware of the variety of organic structures and we know about the existence of isomers, hopefully you already know that it is very important to be able to clearly represent structural formulas. We need to think about structures as the language of organic chemistry. Now, there will be times when you need to think about the 3D shape and you need to represent the 3D shape of a particular molecule, but often we will be able to use the full Lewis structure, also called the Kekulé structure, that we first talked about. So let's look at an example. So we have 3 carbons and then an oxygen connected to our hydrogen. So this is an alcohol functional group, and this compound is called 1-propanol. And what we have here is our full Lewis structure with the line representing a pair of shared electrons, and we draw in all of the atoms, including all of the hydrogens. A different way that we could represent this is called a condensed formula. This molecule could be written as CH3, CH2, CH2OH, and we typically don't include the lone pairs, or it could be further condensed as CH3 parentheses CH22OH. So this tells us that we have 2 of these CH2 groups in between this carbon and this oxygen. Another way that we can represent structural formulas, and this is really a lot more of a shorthand, is called a skeletal or a line bond structure or a zigzag structure. And this one would look like this. We should still include our lone pairs, but notice we don't include our carbons. Each zig or zag is a carbon. So this is a carbon at the end, this is a carbon at this top zigzag, this is a carbon at the bottom zigzag, this carbon is connected to this oxygen. So we don't draw our carbons, we do draw other atoms. So oxygens, nitrogens, sulfur, halogens, those will all be drawn. We also do not include the hydrogens that are connected to the carbons, but we do include hydrogens that are connected to any other atom. So the skeletal or the line bond, you need to mentally fill in all of the carbons, you need to mentally fill in all of the hydrogens, but by the time we're drawing a lot of molecules, you're going to appreciate having this shorthand. Now, another option is kind of a combination. It's somewhere between a condensed and a skeletal structure. In general, I like to use the combination structures. I think of them as kind of a blend between a condensed and a skeletal, but they have more detail than either one of these, but they're less cumbersome to draw than the full Lewis structure. So for this compound, the combination formula would look like this. We have our CH3 connected by a single bond to CH2, single bond to CH2, single bond to OH. So let's look at a different example. If we have propene, we could have our first carbon connected to 2 hydrogens, double bonded to a carbon, connected to a hydrogen, and connected to another carbon that is connected to 3 hydrogens. So this would be the full Lewis structure. For the condensed formula, this would be CH2, CH, CH3. See, this is where it gets a little bit confusing because we don't explicitly show our double bonds. Even though I've been doing this for a few years, if I look at a condensed structure like this, I don't automatically see the structure. I still need to kind of translate it into a skeletal or combination formula. What does this look like as a skeletal? So we have a zig or a zag for each carbon, and we do explicitly show multiple bonds, but we still don't show the hydrogens. So this is our double bond between the first carbon and the second carbon, and here's our single bond to the third carbon, and we would have to mentally fill in that this carbon has 2 hydrogens, this carbon has 1, and this carbon has 3. Now, sometimes as you are working with a skeletal structure, you might want to count hydrogens. And so if you had this and then you filled in your hydrogens like this can be useful, but this is not a correct representation. If you are going to show your hydrogens, then you must show your carbons. If you don't show your carbons, then you don't show your hydrogens either. Finally, if we think about our combination formula for this one, we would have a CH2 double bonded to a CH, single bonded to a CH3. So if I ask you for a full Lewis structure, then you need to give me this. Otherwise, if I'm asking for a particular molecule, it's fine for you to use any of these representations. You'll also need to be able to read and understand any of these interpretations, because what I use might be different from what you see in lab, and that might be different from what you see in the textbook. So practice drawing structures, practice translating structures from one to another, and that will be really, really helpful for you to gain proficiency. Next, let's practice with a few more structures. So looking at this first compound, this is the skeletal or zigzag formula. So what this means is that we have a central carbon connected to a carbon and another carbon and another carbon. So if we write this out as a Lewis structure, we have these 4 carbons, and then we have to fill in the hydrogens, knowing that carbon likes to form 4 bonds. And the central carbon is also connected to 1 hydrogen. If we show this in a combo formula, this is going to be a CH3 connected to a CH, CH3, CH3. If we did a condensed formula, we could have CH3, CH. It might be shown as parentheses to represent a branch, and then the third CH3. So this means that this carbon's connected to this carbon is connected to this carbon, and then this carbon is branched off of this carbon. Sometimes you will see a semi-condensed formula. So these 3 will be condensed, but this branch will be shown more explicitly. But sometimes you'll see it even more condensed, where you will write the CH and then in parentheses 3 CH3 groups. So the way we're focusing on this, it's like we're looking at this CH connected to 1, 2, 3 CH3 groups. For our next example, let's take a look at this alcohol. And we have our oxygen is connected to a carbon, which is connected to 3 other carbons. I'm not going to do the Lewis structure. Let's just go ahead and look at the combo, where this central carbon's connected to CH3, 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 or focusing on this group right here, we can also write it CH3, CH3, CH3. This is emphasizing the fact that this carbon is connected to this carbon, and then these hydrogens are outside of it, which is helpful. But we are allowed to show it this way because the understanding is that, of course, this carbon is not connected to the hydrogen and then the carbon. We know that these hydrogens are on the outside, even though we write them as if they're on the inside. So either one is allowed. Oops, and I forgot to do my lone pairs here. We should still include those. Another thing to consider, whether we are doing the zigzag or a combo or some other version, if we are writing our OH group on the left, we must have our hydrogen on the outside. Okay, we're not allowed to write it like this. Okay, so somehow we're allowed to do this because everybody knows that we know that these hydrogens are not connected to multiple carbons, but yet writing it this way, you're not allowed that assumption that this hydrogen is on the outside. So this one is not allowed. If you have your OH written on the left, make sure you have the H on the outside. And one more example. So let's notice the difference between this alcohol and this alcohol. So this alcohol is connected to this carbon. So the oxygen's connected to the carbon, which is connected to 3 other carbons. Here, the oxygen is connected to a carbon that's connected to this carbon that's connected to 3 other carbons. So if you're drawing this, you need to be careful with how you show your bond to the oxygen because you want to be clear about whether there is another carbon or not. So this one would be CH3 connected to C, CH3, CH3, CH2, OH. All right, so this is another carbon, and so that's why this is here, and it's not the same as this. Let's take a look at a few more examples using different representations. So here we have CH3 connected to CH2, connected to O, CH2, CH3. So as a combo, we could write this as CH3 connected to CH2, connected to oxygen, connected to CH2, connected to CH3, and let's include our lone pairs. Or as a shorthand, we could write it like this, where our central oxygen is connected to 2 carbons over here and 2 carbons over here. So that is this compound. Next, if we look at this one, well, again, we have the CH3, CH2, CH2, CH3, but now we have a CO. So this carbon must be connected to this carbon, which is also connected to this carbon. So we have CH3 connected to CH2, connected to C, connected to CH2, CH3, and then this carbon must be connected to an oxygen, and to have enough bonds, it must be a double bond. So notice with a condensed formula, they kind of look similar and you might easily overlook that carbon, but if you have this type of structure, it's really easy to see the difference. And we could also write it like this if we were to use the zigzag structure. Here we have another 2 compounds that look kind of similar. They're both CH3, CH2, CH2. This one is OH and this one has the CHO. But they have very different meanings. This one is what we were just looking at a few slides ago. So this is CH3, CH2, CH2, OH, or the 1, 2, 3 carbons connected to the OH. And that's this one. And now this structure, we have this carbon connected to this carbon, connected to this carbon, connected to this carbon. This carbon must be connected to this hydrogen, and this carbon must also be connected to the oxygen because the hydrogen can't actually be in between the carbon and the oxygen. So what does this mean? We have CH3 connected to CH2, connected to CH2, connected to C, which is connected to H, and connected to O by a double bond. And then we could write this like this. But wait a minute, let's double check because this says I have 1, 2, 3 carbons, but I actually have 1, 2, 3, 4 carbons. So I stopped my zigzags too soon. We have the CH3, CH2, CH2, C, double bond O, and we do draw the aldehyde hydrogen. So this functional group is an aldehyde where we have a C double bond O and that C is connected to a hydrogen. So normally with our zigzag rules, we don't draw the hydrogens connected to carbon. We don't write this carbon, we don't have to write this carbon explicitly, but we do write this hydrogen explicitly. So make sure you get lots of practice drawing structures with different representations.